It's more like note to self.
Oh no, that's not documentation.
It's documentation to self. This was back in the .com boom days. It was close to the end of the boom. It's almost the beginning of the bust. So I was hired by one of my ex-roommates from UC Davis, and he was running a company. And this was the time when they ran out of experienced programmers. Okay, so they started to move on to graduate students, and then they soak up every single graduate student. Even graduate students from Davis got soaked up. Then it went to undergrad students. Many undergrad students actually suspended their study to work for these companies because it was good money. And then they ran out of those students too. And then they moved on to high school students. So they approach high school students who claim that they can do PHP coding and whatnot. And then they say, okay, so how can I convince you to work for me? And remember, we are talking about high school students. We're not talking about somebody who has, like a resume that is really long and has worked on multiple really, really difficult and challenging projects. So we're talking about high school students, who have not graduated yet. And then they offer these things like, okay, just name your price, okay? What kind of fancy chair do you want, in your office? Maybe that one. $2,300? Yeah, we can afford that. What else? I want to cater lunch and dinner. I want someone to pick me up to go to work, and so on and so forth. That was basically how it was like at the end of the .com boom back in the late 1999 and early 2000. It was like that. And we had a lot of people who basically was coding and reading how to how do you call those books? PHP for dummies, right? And the CD-ROM is in the computer so they can copy and paste the code.
That sounds about right.
Yep, and that's how a lot of websites are hackable. It's not because of a server issue, it has to do with the scripting on the server. The server itself can be bulletproof, but because of the scripts did not take into consideration of SQL injection and all kinds of stuff like that, they become easily hackable. You can just dump the entire table of credit card numbers and whatnot, and people were storing passwords in plain text, not even MD5 hash. Okay, MD5 hash is already bad enough, but it's just like plain text. Yep. So that was about 18 years ago. The 2000 .com boom.
And how much has that changed since look at Equifax for example?
Well, the question is how much code developed back in those days is still used on servers today. The more obscure the server, the more likely some code from all the way back then is still running. So there is that. Okay, cool. So we're going to go to the dashboard. I don't like this. I'm going to switch it back like that. And we go to the lecture today. The cricket is back, by the way. The cricket is back. Okay, so last time we talked about ROM. So what we'll do today is talk about RAM. RAM is a little bit more challenging. So we are basically on this particular topic now. RAM is a little bit more challenging because ROM is read-only. Okay, so it's either the ROM itself is not selected, or it is selected, it's paying attention to the address bus, it is addressing whatever location the address bus is indicating, and then the content of that location becomes the D port output. Okay, so that's relatively easy. When we look at RAM, it is a little bit different. Okay, so let's go ahead and take a look at RAM documentation, and I'm going to use the web page for Logisim instead of inside Logisim itself, because I think this scales a little bit better on the screen, so that's why I'm using this one. So we go to memory, and then we click on RAM. So that's going to be the first component that we'll be talking about today, is the RAM component. So for the RAM component, we are going to use, well, okay, let's ignore those pictures. And instead, we'll go ahead and run Logisim, and I want to make sure that OBS is actually recording. Yep, it is. Okay, so let me start up Logisim first. Java jar, Logisim. There we go. Because this is more interactive, I can actually poke stuff in the RAM module and stuff like that. So we go to memory, we select a RAM module, and then we just put it here. Okay. So the first thing we want to do is look at the attributes of a RAM module. So when you look at the RAM module, it has got three things. The first two are identical to a ROM module. In other words, you can change the number of bits allocated to the address bus. In other words, the width of this particular port can be changed. Whatever this number is, okay, so let's say I change it to 5, okay, for whatever strange reason. That means the width of the A port is now 5 bit wide, but that port controls the number of locations that are addressable. So now the question is, with 5 bits to specify a location, how many locations can I actually address? What do you guys think? It's 5 bits, which means the first location is 0, 0, 0, 0, 0. The last location is 1, 1, 1, 1, 1. So how many locations are we talking about? 32, because we have to include location 0. So, but yes, it's related to 2 to the power of 5. Okay. The second attribute controls the width of each location. So they are completely independent. In other words, the width that you choose for the address bus controls the number of locations. 2 to the power of whatever you choose for the address bit width controls the number of locations. But the size or the width of each location is controlled by the data bit width. Okay, the default is 8 because 8 bit is 1 byte, but you can choose some really oddball width if you want to, like 13. Okay, for no particular reason, I'm using 13 bits, as a width for every single location. Okay, is that okay so far? Okay. So when you look at the content now, you can see how each location is represented by 4 hexadecimal digits, because you need 4 hexadecimal digits can address or can specify up to 16 bits, but 1 fewer is not enough. So that's why there are 4 hexadecimal digits to specify the content of one single location. And then when you right-click on this and go to Edit Content, it will show you this window. I know it's kind of small and not easy to read from people in the back may have a problem reading this, but you can basically see that we only have 32 locations, because on one row, we have 32 locations, because on one row we have 16 locations, and there are only 2 rows, so there are 32 locations to be exact. So are we doing okay so far with attributes of the RAM? This part is common, by the way, with ROM, okay? So I can do the same thing with ROM as well. The third attribute is not shared with ROM. The third attribute has to do with how we specify the data interface. And right now it is selecting one synchronous port. And what it means is we have one single port for data, and it is synchronous in terms of operations. Synchronous means, when we want to perform a read operation, it is instantaneous. Okay, when it is selected and we specify a read operation, then the data is going to the output immediately. When we want to write, it behaves kind of like a register. It needs the clock signal to have a rising edge in order to clock in, or in order to store the content into the RAM. Okay. So now would be a good time to look at the other ports. SDL is select. Most chips actually do not call the select line the select. It's called chip select, or abbreviated as CS for chip select. So for those of you who are moving on to a computer engineering major, just kind of keep that in mind, that SDL in this particular document, in this particular nomenclature, is usually known as CS or chip select in an actual chip. It serves the same purpose as the select line of ROM. It's basically saying, okay, should this particular chip be paying attention to everything else? So if select is 0, it means this particular RAM chip is not doing a single thing. It's ignoring everything. It's ignoring all of the other pins, it's ignoring the address port, and it's not doing a single thing with the data port. It's not going to drive the data port. Is that okay? So the select line is kind of doing the same thing as in ROM, but then we have 3 additional ports that are missing in the case of a ROM. So we'll go through each one and talk about what each one does. And I'm going to go to the first one because this one is easy. This one is the same thing as the pin that is labeled 0 with a register. In other words, when this pin is asserted, it will clear the content of RAM. So it's the same thing as a reset, for registers. Is that okay? Yep.
Does it clear all of everything in RAM or only that particular?
Every single location.
Oh.
So when clear is asserted, it will clear the entire content of this chip. Is that okay? We can demonstrate all that stuff too. The next one is load. Okay, this one is misleading because it's actually controlling whether we are reading from RAM or are we writing to RAM. Okay, if it is a 1, we are reading from RAM, which means the D port is driving the output when the chip is selected. If LD is a 0, we are writing to RAM, which means the D port serves as an input. And when we have a rising edge at the clock and the select is a 1, and then the A is specified, it will basically read whatever is at the D pin here, and it will update whatever location is addressed in order to perform the write operation in this case. The one pin that looks like a little wedge serves the same purpose of the same pin on the register. It is the clock line. When this has a rising edge, then when we specify a write operation, at that moment, whatever is presented at the D port is going to be stored to whatever location is addressed. So it does share a lot of common elements with the other components that we have talked about. It's kind of like a combination of a ROM and a register, if you will. Is that okay? All right, so what we'll do first is we'll go ahead and interface with this thing, with some input pins and output pins, and then we'll try to see how we can store content into RAM first, okay? And then we'll start to retrieve the content from RAM. And I'm going to change it back to kind of the default, okay, which is 8-bit wide for the data bus, for the address bus. So we have 256 locations. And then each location has exactly 8 bits, which is a single byte. There we go. And then we'll just draw some pins here. This is the address pin. It's connected to here, and obviously it's going to have a problem because we need this to be 8-bit wide. There we go. And I might need to zoom out just one level, just because this is going to be.
The load, you said 1 means, or 0 means read or write?
0 means write to RAM, and 1 means read from RAM. Because when we specify read or write, we have to be very clear about from the perspective of which component. All right, so at this point, D is going to use an input pin. Okay, so here's another input pin, but I'm going to change the heading or the facing to west so that the pin or the connection port itself is on the west side instead of on the east side. And we also have to change the width to 8 bits to match that of the RAM. And then we just have a whole bunch of single pin here. I'm just going to have a whole bunch of single bit pins to connect to the rest of the RAM module. So to be exact, we have 4. So this way we have a pretty general design and we can just kind of play with this any way we want to. So here's the select, here's the clock, this is the read-write control, and this is the clear, or also known as the reset pin. So now we can just kind of play with this, okay? So let's just say that I want to change location 10, okay? Location 10 in hexadecimal. I want to change location, not A0, 10. Let's change location 0A, which is actually 10 in decimal. So I want to change location 0A to, I don't know, 4 or 5 in hexadecimal. How do we do that?
First
Okay, so-
identify the address.
Huh?
First identify.
Okay, first identify the address. So the address that I want to get to, or the location, is 0A in hexadecimal. So what do I need to specify in this picture to specify that address?
0, all 4 zeros.
4 zeros, and then
0, 1, 0.
1010. That is correct. Okay, and which input pin should we be modifying? The one to the left or the one to the right? The one to the left, because it is the address. So remember, the address port is kind of like what you put inside square bracket when you use array indexing. Okay, it controls which element in the array are we interested in. Okay, so we'll specify 1010. So change it to the poke tool. Okay, we got 1010. And nothing is happening because when a byte or when a location is selected or when it's addressed, it would at least be highlighted. I don't see that location highlighted. Why not? Because the chip itself is not selected. In other words, as far as the chip is concerned, it doesn't know that it is supposed to pay attention. Okay, fine, we'll tell you to pay attention. You can see how the select line, as soon as the select line is 1 or asserted, the location that we are addressing is immediately highlighted. Okay. What about the 4, 5, the actual value that I want to store to that location? How do we specify 4, 5 in binary? 4, 5 should be pretty easy.
Wait, 4, 5, is that hex?
Yeah, 4, 5 is in hexadecimal. So what is 4?
0, 1, 0, 0.
Okay, so we will put a 1 here, and then we have 5, which is
1, 0, 1.
0, 1, 0, 1. Very good. Okay. So we now have 4, 5 here, and I don't see that location changing. Why not? Because we need a rising clock, and we also want to make sure that LD is a 0. Because if LD is a 1, it is actually going to output the content of that location. But since we are going to change that location, we have to make sure LD is a 0. And we also need a rising edge at this time, and now it updates the content. Now, it is edge sensitive, which means after the rising edge, I can now do whatever I want with this input pin, and it doesn't do a single thing. Okay? Is that making any sense? So from that perspective, it behaves just like a register. Okay? After the rising edge, once it updates the content, it just completely ignores the input. Is that okay?
So D can be both input.
Exactly. This is one of the very few devices that we'll use in this class that can serve both, where it has one port that can both be output and input, but not at the same time, obviously. Okay. So let me ask you this question. What is going to happen if I turn off select? The highlight is going to be not going to be highlighted, but the 4, 5 will still be there, right? It is just not selected. It's just, yeah, okay. That's exactly what happens. And obviously, when the chip is not paying attention, we can clock whatever we want. It's not going to do a single thing. So here's the next question. I'm going to change the load line from a 0 to a 1 to basically specify that we are now specifying a read operation from the perspective of outside of the RAM. And then I'm going to go click on this line here to say that, yep, memory chip, pay attention now. What do you think is going to happen?
Yeah, because you have.
It will attempt to change the output to 4, 5, which is 0, 0, 0, 1, 0, 0, 0, 1, 0, 1. But the input pin disagrees, right? The input pin is saying, oh, somebody else outside of this chip is currently specifying the content of that wire to be 11010011, which is disagreeing with what the RAM chip is going to want to specify. Okay, so before we click this, we want to confirm that that is indeed the content of this chip. I mean, on that wire. So this wire is specifying 11010011 because it's connected to the input pin, and -45 is the signed interpretation of those bits. Okay. All right, so now we're going to change the select from 0 to 1, and we end up with a red wire. Because now we have a bus fight, So I looked it up. I looked up the term bus fight. It is actually not the official term. The official term is bus contention. But I much prefer the word bus fight because bus contention or contention typically does not end up in death. And the bus fight typically would end up some components getting permanently damaged. So so bus fight is actually more appropriate as a term. I think, but bus contention is way too polite. It does not convey the urgency of the situation. Yep.
So you only need to activate the clock when you're reading or writing?
Yes, the clock line is only used when you're writing. When you're reading, it is not used. Yep.
So to fix this, would you, when the load is 1, would you have a function or a gate that would nullify whatever would change that output?
Yes, you need a clutch. Yeah, you do need a clutch. So what we're going to do next is actually click on this wire because not every single bit is being disagreed. Okay, because remember the RAM module is trying to output 0, 1, 0, 0. And then the input pin is specifying 1101 for the most significant 4 bits. And you can see how the middle 2 bits are actually not in contention because both the input pin and also the RAM is trying to specify a 1 and a 0 for the 2 middle bits of the most significant 4 bits. And the same thing applies to the most significant bit and the least significant bit of the least significant 4 bits. The E's are indicating the ones that are disagreeing. Okay, so this is really useful when you're debugging a design. The red wire is really helpful. Click on it, and it will show you why it is red. Okay, which bit positions are in contention right now. So are we doing okay so far with this? All right. Okay. So we want to change the situation so that we would not have this problem. So the component that you need to change this entire situation is in gates. It's called a control buffer. Okay, so there are two buffers. There's one buffer here. Okay, I'm going to put it here just so that we can see how they are slightly different. And the other one is a control buffer. Okay, so when I zoom in, yep, go ahead.
Just a quick question. The clock, when it's reading from RAM, the clock doesn't need to be set for it to read, right?
When you're reading from RAM, the clock is completely ignored. Okay, so when we look at these two buffers, you can see that one buffer only has one input and one output. The other buffer has one input, one output, and a control line. So can someone kind of guess what a buffer is? What does it do in general? Not a control buffer, which is what we need, but a general buffer. What do you think it is used for? Say that one more time. Stop the signal. No, it's not for stopping the signal. Yep.
Maybe delay one signal such that they don't get to.
It does have a delay, but that's not why we want it. In fact, we want it to not delay, but it does have a delay. Yep.
Does it store data?
Nope, it does not store. It is nothing more than a hub or broadcasting or an amplifier. Okay, the best way to look at a buffer is it is an amplifier. Okay. If you have an incoming signal, if you have one single wire that has to fan out and connect to, let's say, 200 inputs to other chips and other components, you can do that in Logisim because Logisim doesn't really emulate the physical aspect of a circuit board and also electronic circuits. But in reality, you cannot do that because what happens. Okay, I'm hoping you guys do remember the picture. I can just draw that on this whiteboard because it's not going to be twist on, so I can just draw here. Okay, if you remember, okay, that doesn't work. Let's try this. That works. Good. Okay, this is a transistor. Okay, whether it's an N or P doesn't really matter. Okay, this is the gate, and it doesn't matter which one is the source and which one is the drain. Okay, it doesn't really matter for the purpose of this discussion. So this is one, and here's another one, and here's another one, and so on. So let's say the output of something is connected to all of these inputs. Okay, what the circuit needs to. In other words, this is not erroneous. But just imagine that you have 200 of these things connected to the single output of something. Okay? What do you think is going to be the problem, the physical issue with this particular scenario?
It reduces the current.
Sorry?
It reduces the non-current.
It reduces, well, okay. When you look at this, what does it look like? If you just kind of focus on this part of the circuit, what does it look like? For those of you who have taken classes in physics, in electrical circuits, what does it look like to you? It doesn't look like a resistor. A resistor has all that squiggly line. It doesn't look like a light bulb. It doesn't look like a capacitor. Looks like a capacitor. Very good. Okay, so it does look like a capacitor like this because we have a gap in between, and then it does form capacitance. In other words, every single input to any gate or any chip has a certain capacitance associated with it. And how does a capacitance influence the state change on an electrical wire? In other words, on this side, I'm giving you a square, okay? And then on this side, with 200 of these things connected, what do you think it's going to look like? It's not going to be a square wave anymore. It's going to smooth it out because that's what capacitors do. Is they kind of smooth out the circuit with in combination with resistance and stuff like that. Okay. So on this side, if you connect too many of these things, your curve is going to look like it's going to be much rounded like that. Okay. Now, if you take inductance into consideration, it's going to be even worse because it will look like a shark fin. Okay, it's going to look like a. Okay, let's see. No, it's going to look like this, and it's going to look like that. Okay, because of inductance. So when you combine inductance and capacitance and stuff like that, what software people would say, oh, it's going to look like this because the circuit is perfect, and these transistors have no capacitance, the wires do not have any inductance nor resistance. This is the software perspective. Okay, programmers see it like this. Electrical engineers, on the other hand, will look at it as a shark fin. And I think it's going to look like this because it has a sudden drop. Why do you think that is going to be a problem? What is going to happen to things that are quote-unquote edge sensitive? What is the whole purpose of being edge sensitive? To control the timing, right? The timing can be very precise. If the wave is like this, we can say that, oh, within a very, very small margin, okay, we know everything is going to be updated within those nanoseconds. Okay, which is good. But when you have a shark fin, it's not an edge anymore. So when is your register going to update when you have a shark fin signal like that? Well, it depends a lot on the characteristic of each individual device then. Some devices may update at this time because when it crosses over from this voltage to this voltage, it wants to update. Other devices may want to update at a later time, and so on. So now you have timing issues that did not exist before. So we do not want to degrade a square wave into a shark fin. And yep.
I was going to ask what happens when it actually drops below the 0 line as well.
It doesn't do a whole lot. It's not damaging per se because the time in this kind of negative notch here is really, really small. So we're not talking about a significant amount of energy because of that negative notch. So the negative notch is there because it does look really bad on the oscilloscope.
I was just going to say it's a non-zero now, so
sorry?
It's a non-zero now.
It will still be quote unquote zero, considered zero, but it just looks really, really bad because you have a notch. The notch is due to inductance. Without the inductance, it wouldn't be like that. So what is the fix of this problem? The problem has to do with one single driver is connected to 200 or more input pins. So what we want to do is we control the fan out ratio is too high. That is the problem. Okay, so we want to limit we want to control the fan out ratio. So that means we can use buffers. So instead of having one single device to connect to 200 devices, we have that thing to output to a bunch of buffers. And each buffer doesn't really do a whole lot. It's a fairly dumb device. It just reads whatever is in the input and it sends it back out to the output. But it does amplify, quote unquote, the current. So by using this method, and if you stage like even stages or hierarchy of these things, then the timing will now be predictable again. Because each one, the end result is we want each buffer to only maybe have a range fan out of 10, 15, inputs. But through the use of buffers, that can be done. So that's the main purpose of using a simple buffer, is basically to deal with physical issues on the circuit board when you have a high fan out ratio. Is that okay? All right? But what we want is not a regular buffer. What we want is a control buffer, which means the output can be off. So what we can do now is to look up the documentation of a controlled buffer. It's a pretty simple device, so the explanation should be really, really short. So we go to buffer, and it's a control buffer. We don't want an inverted version, just a regular control buffer. Yep.
Does the buffer, if it's stronger, does it override whatever the previous in the data slot? If there was some, if it's reading from RAM and there's something in the data slot, and does the buffer, if it's stronger, does it override whatever's in there with the?
You don't want the buffer to be active when the input pin is
right,
active.
When
yeah, only one should be active. Yep. So you basically want to control, which one is. You want to control which one is driving the quote unquote bus. Is the RAM driving or is the input pin driving?
Yeah, once it's like controlled, yeah. So it does override it?
Does it what?
Does it override whatever previously?
No, I don't think so. It is. Are you talking about overriding or overwriting the content in the RAM or just on the wire?
In the data, in the output, in the data output.
You mean the wire?
Yeah.
When the controlled buffer is on, whatever content you specify with the control buffer will drive the output. And if that output is connected to the wire will have the content of whatever the control buffer wants to output. Okay. So we are looking at the documentation here. It's called a 3-state buffer. Each one has a 1-bit control input pin to the south side. The value of this control pin affects how the component behaves. So that pin that is coming out of the middle part of the triangle is going to do this. When the value of this pin, the control pin, is a 1, the component behaves just like the respective component, either just like a regular buffer or an inverter, which is inverting the input, is a NOT gate. When the value is 0, then the component's output is floating. In other words, it's not going to drive the output. Okay, so that's what we need in order to make the circuit not to have this erroneous state. So what we need to do now is to get rid of this wire. We know that we need one of these things, okay? And now the question is, how do we control the control buffer here? Yep.
If you don't hook it up and you just hook up just the control and turn that on and off, will it go from red to blue on the pointing part of the buffer?
Okay, so let's do that. It doesn't know what the input is at this point because no one specifies the input, so it is still blue, which is basically saying, okay, it's undetermined. Nobody told me what the input is supposed to be, and as a result, I cannot tell you what the output is supposed to be. Okay, so but this is not the circuit that we want. Okay, we need something different. Okay. So we know that this is going to be coming from here. Let me think about this. The other way around. Okay, so we will turn this to face west because we want this to be we want the input pin sometimes to specify the data port, but sometimes we don't want the input pin to drive that port. So the direction is going to be like this. And we also want to invert the control line so that it is the other way around, like that. Okay. So now we can specify this. And well, we can fix the width too. We can turn this into a multi-bit controlled buffer. That fixes that problem. So now the question is, how do we control this line here so that when we are reading from the RAM, the control buffer, it will say, okay, let's not drive the output because the RAM chip is driving the output. But on the other hand, when we specify a write operation, then we want the control buffer to turn on and say, whatever the input pin is specifying, let's store that into RAM.
Can we negate whatever's coming from load?
The negation is correct. Okay, so what are we negating?
The signal coming from load?
Load. So we're negating load, and then the negated line goes into the control buffer. So this is how we do it. So at this point, okay, if you tap this wire, okay, so let me tap it to an output pin. You can always have output pins connected to stuff. Okay, that is always okay, because you just want to check out what is on that wire and make it easier to understand what is going on. So now we can specify this to be 8-bit wide, and you can see how when we, okay, let me zoom out one level. So you can see how when we are reading from RAM, this is actually 4/5 in binary, okay? On the other hand, if I turn it off entirely, or turn off this operation, excuse me, if I turn off this pin and specify a write operation, you can see how the input pin now specifies this wire, which also goes into the RAM. So it solved that problem, basically.
So you would need an additional output slot.
Sorry?
So you would need an additional output.
An additional output.
Or like, you have the second window of the output to actually, when it's reading from RAM, to actually display what it's reading from RAM.
Correct. Yeah, so this wire typically goes to a lot of things inside the processor. So we do okay so far with the two cycles of RAM. The read cycle, how do we read from RAM? And the write cycle, how do we change the content of one location in RAM to something else? So are we good with that? So far so good? Okay. So if I go back to the class, basically the module description here, the next thing we need to do is to look at mux and demux. The terms are very intimidating, but they are very, very simple devices in a way they're very simple. So we'll take a look at the picture of a multiplexer and a demultiplexer. It looks like this. And it is, when you read the description, it's kind of intimidating because there are a lot of different pins. So instead of doing this, I think I talked about Thomas Train the other day, right? So we'll look at Thomas Train, how do you call this thing? Oh, track switch. There we go. And this is, would you pay $24 for this?
I have paid 20. No, I'm just kidding.
I think they have one that actually has a switch. This one doesn't have a control, so I want to look for one that actually has a control. So let me look for another image here.
But it's free shipping.
It's free shipping, yes. Now they have ones that actually have a slider, like this one. There we go. Okay, the red piece is the one that I want to talk about. So let's go ahead and, how do I look at just the image itself?
Stop doing that.
Yeah, they stopped.
Why would they stop doing that? Because everybody's doing it. Man, that is so lame. Okay, so can I do this? View image. There we go. Okay, here's your multiplexer. That's all it does. Okay, it's a switch. The two terms, multiplexer versus demultiplexer, is just saying which way is the train coming. Okay, so and I can never remember which one is which one, so we'll look it up. So multiplexer is multiple input and one output. Okay, so a multiplexer. Okay, let me go back to the picture here. So multiplexer is basically the train. You can have multiple trains coming in from the multi-side, but there's only one train. There's only one output. It outputs to one single track. It concentrates multiple tracks to one single track. That is a multiplexer. Yep.
I was just thinking, what happens to the other train? So what happens to the other train? It disappears?
Okay, so you don't want to end up with a train contention.
It's a train thing.
So if you do have multiple trains at this junction, because the trains are all coming in, so the trains will basically, they can all stop right before a multiplexer, but only one can get through. The one that can get through depends on which way you switch the multiplexer. So you can have a 4-input, 8-input multiplexer, and you can have 8 different signals coming in, okay? But by using a 3-bit selector, so the selector is going to be a little bit more elaborate in this case, you control which train gets to go through the switch. Is that okay? Yep.
So it's basically like the address port in the RAM?
In a way it is, yes. In a way you can kind of imagine that there's a really, really big multiplexer that selects which location of RAM becomes the actual output. Yes, so you can look at it that way. Yep. All right, so are we good with what is a multiplexer? It's basically a selector, a switch, okay? And then if you look at it from the opposite perspective, it becomes a demultiplexer. In other words, you have one single train coming in through the one track side, and the switch is now saying, okay, we have multiple destinations that you can go to, tell me which one you want to go. That becomes a demultiplexer. So demultiplexer has one single input, multiple outputs, and then you have the selection pins to say, okay, which one should we be using? That becomes a demultiplexer. So a multiplexer is a concentrator. A demultiplexer is just saying, okay, which way do you want to go? It's a selector. Let you select which way to go. So are we good with that particular term? And there's one more, okay? There's one more which is related to a multiplexer, a demultiplexer to be exact, but it's not called a demultiplexer, it's called a decoder. So when you look at a picture of a decoder, don't you think this looks like a demultiplexer? Let me show a demultiplexer first. So here's a demultiplexer. You can see how you have one input and multiple output. Let's zoom in and see that in details. So in this one, you have one single input, you have 4 outputs. That's a demultiplexer. And then we go take a look at a decoder. Zoom in again. And you can see how the decoder has 4 outputs, but there's no one single input because the implicit input is a 1. That's all. In other words, a decoder is really just saying which one of the outputs is supposed to be a 1. Everybody else would be zeros. That's what a decoder does. And then the input or the select, I think the select is from this pin here. No, I take it back. The select is from this pin, the pin that has a gray dot on it. This will require a 2-bit select. Because in order to select 0, 1, 2, or 3, you will need 2 bits to specify that. So the gray dot is what you put inside the square bracket in array indexing, and this will be the content of that particular array element. So you can look at it as array address, array indexing again. Are we doing okay so far with the multiplexer, which is a concentrator, the demultiplexer, which is a selector, okay, one input and which way do you want it to go, and a decoder, which is basically the same thing as a demultiplexer with a fixed input of a constant 1. Is that good? Okay. So if that is all good, then we are ready to look at the processor. The processor is in the shared drive. So if you go back to the shared drive link at the top, the share folder. So I'm going to open this in the new tab. There are several files you have to download to make it work. So I'm going to show you guys exactly which files you will need to get the processor to work. Alright, so you go to processor, which is a subfolder of the share folder. And once you get there, there are several files. And all of those files that you need to make this run, they're all ending up with CIRC extension because they're all logic.sim files. So the first one you need is ALU.CIRC, and you can use a control click to select multiple files. So the next one is register bank down here, regbank.circ, and the last one is going to be processor wdpc2.circ, which is this file here. So these 3 files you will need in order to get the processor to work. Are we okay so far? You know, which 3 files and how to multi-select the files. I mean, you guys know how to control click, right? Hopefully, yes, hopefully. Okay, so now that you have selected multiple items, you can just go ahead and download. So I think just click on right-click on any one of those and click download, and it will download as a zip file. I mean, you guys know that part too. So once you have the file, you just go ahead and unzip it, and then I'll show you what to do with the content after you unzip.
How do you unzip it?
In DAWs? Okay, so I'm gonna save the file to the temp folder. I'm gonna rename it to processor because there's no way I can remember the other name. Okay, so I'm going to switch to a terminal. Oh, not that one. Not that one. I used to have a large terminal. What happened to it? Oh, okay, it's right here. There we go. Okay, so you just unzip it. Okay, make a folder first. Personally, I would make a processor folder first and put everything inside the processor folder. So I'm just going to unzip processor.zip. Okay, 3 files, pretty easy. Then you switch back to logic.sim, which I already have opened, and you can always just file and then click open. What this will do is it is not going to forget what is already here. It's going to open up a new instance of logic.sim. So when you click open, you go to the folder where you decompress everything, and it's the temp folder for me. It turns out to be a little bit more cumbersome to get there, but we'll get there. There we go. And the file that you want to open, now this part you have to kind of pay attention because you want to open processor dot blah blah blah. Okay, the name can change because I have different revisions and whatnot. But this is the file that you want to open, not the other 2. When you open this one, it will say, it doesn't ask anything. This is the processor. This is a simple processor. Let me emphasize, this is a simple processor, but it has everything component in here you already know. Okay, here's a ROM, and this is an adder, this is a register, this is a very simple multiplexer, 2 input only. Here's a splitter, this is a tunnel, lots of tunnels. Then you go like, but what exactly is this? This is a register bank and this is an ALU, so those things are not standard. But when you expand it, then you go like, oh, okay, I can see what it is. Okay, it has got input pins, right? It has got a decoder. It has got registers. It has got 2 multiplexers and output pins, and then we have some control pins as well. In other words, everything in this processor are made up of components that we have either talked about today or talked about previously. The ALU, on the other hand, is going to do all the processing, and this is what it looks like. It is a little bit larger than the processor bank, but we have input pins, okay? We got demultiplexers, we got actual adders, subtractors. This is a right shift operation. This is bitwise NOT, this is bitwise AND, and this is bitwise OR. Okay? And then on the other side, we have a multiplexer, and then we have an output pin, and that's basically the main part of the ALU, but it has got some other stuff down here as well. Okay? This subcircuit here, how many of you recognize this subcircuit? It has got 3 inputs, right? You know, there are not a whole lot of circuits that we have talked about that need 3 input AND gates. Yep.
It is
A C flip-flop has feedback, has the wires going back. This one does not. This is not an SR latch because SR latch also has signals going back. This is the overflow. Very good. Okay, so this is the overflow circuit for the subtractor. This is the overflow circuit for the adder. And they are different, okay? Because the way you overflow is different when you're subtracting compared to when you're adding, okay? And then we got more multiplexers down here, another one down here. And then we got one really kind of interesting thing here. This is, what do you think this one is gonna do? Just focusing on this part of the circuit, what is that gonna do? This is a NOR gate, is a negated OR gate, right? So if you ignore the negation part, what does an OR gate do? I mean, just in general, it has got 8 inputs. But in general, what does it do? If at least one input is a 1, the output is a 1 with a non-negated version. This is negated, which means the only time this NOR gate is going to output a 1 is when everything is 0 in the input. And that's why it is called a 0 flag, because when the 0 flag is 1, it indicates that the output of the ALU, which is this connection here, is a 0. So we can detect values of 0, you know, easily, just by looking at one single flag. Okay? All right. So, can we start to use the processor now? Okay, so we want to look, when we look at this, right, this processor, you can look at all of these things and go like, wow, this is overwhelmingly lots of stuff that we are happening here. In other words, where do we start? That would be a good question. Where do we start? So personally, I would look at the simple stuff first. Okay. In other words, I'm going to go all the way down here and look at the simple stuff. We can recognize the simple stuff. Let me go ahead and select which one here. This is just a register. Okay, we know what a register is. It doesn't do a whole lot of useful stuff either. Ignoring, you know, that it connects to a ROM, you can see how the register output connects to the input of an adder. The output of the adder goes through a multiplexer, but eventually it goes back to the register. In other words, this is a counter. It is just like a normal counter with an option, right? So the only thing that makes this counter a little bit tricky is sometimes we can use the other input of the multiplexer to update the register. But otherwise, if you just look at the register, the adder, it is just a regular counter. So with a regular counter, it means I'm incrementing something, right? You know, it goes from 0 to 1, 1 to 2, and it has a clock line. This clock line here is shared by all components in this entire, you know, logic set. So when you select the clock line, you can see how a whole bunch of wires get highlighted. So you can see how this one is highlighted, and you can also see how the clock to the register bank is highlighted, the clock to the flag register is highlighted, and even the RAM module, the clock to the RAM is also highlighted. We have one single clock to the entire system. And the reason is because the reason why we have edge-sensitive components is for timing control. And the timing control applies to the entire thing, to the entire design. Okay, so just getting back to that portion, the portion that we were looking at. Okay, so we have a clock here. Unless this multiplexer is choosing this side, this sub-circuit is just incrementing, okay? 0 to 1, 1 to 2, 2 to 3, and so on and so forth. So now the question is, what is that value that we're using for? It's counting, but what are we using the value of the register for? So now we say, okay, let's figure out where it connects to. It connects to the adder, okay? That's part of the deal of being a counter. But it also connects to a ROM, right? It connects to the A part of a ROM, which means it is selecting which location we want to use in this ROM. Is that making any sense? We kind of know what ROM does, right? Except in this case, we have a kind of automated mechanism to control which location we want to address in ROM. Every single clock, it will increment to the next location, then the next clock is going to increment to the next location, and so on. In other words, we have a very, very basic music box, or music, how do you call those things? Music box, right? Yeah. Yep. So we have a very basic music box design where it has a very simple mechanism to rotate the drum, and depending on the pegs on drum, it can play very simple tunes. So now we look at this ROM here, they're like, well, this ROM is kind of strange looking because it seems like the locations are pretty wide. And you are correct about that. The width of this ROM is 26 bits. It's 26 bits wide, and the address bit width is 12 bits, which means we can specify 4,096 locations. Okay? But then the question is, what is the output of this ROM doing? So the output of this ROM is going through a splitter, and this splitter is splitting to a lot of things. Remember, we got 26 individual bits, right? So the 26 individual bits are split into some main portions, like this wire is all by itself, this wire is all by itself, and then the main portion is here. It goes from bit 3 to bit 23, so there are 21 bits going to ucode data or microcode data. Microcode data is up here, and it is going through another gigantic splitter into individual wires like these, individual tunnels. And where do you think these tunnels are going to? Let's click on this one. This is register input multiplexer. So this one goes to the register bank. You can see how this one is highlighted. And now you can understand why I use tunnels. Because if I didn't use any tunnels, the wires would be all over the whole thing. I mean, it would become impossible to read the whole thing. So tunnels really make it easier to read. Okay. So what are you getting out of this design, this particular design at this point? Other than the fact that it is kind of overwhelming. Okay, we got a music box down here. Okay, we have a very basic music box design. Ignore this input from a multiplexer. Just kind of think of it as a basic music box that is clocking through all of these addresses. But the idea is these bits that we specified in the ROM is controlling all of the other components in the processor. Okay? Okay, I'll give you one example. This is another way to start to understand the processor design. Registers basically can be used to store values after computation. So when you're adding, you basically, okay, where do you get the two numbers that you're adding? Where do you store the result of the addition? Okay, that's a question. The register bank can specify the values that you want to use for the addition. So that would be out here, okay, so out 0 and out 1 can be used to specify what you're adding. And you can see how these are not directly connected to the inputs of the ALU or the arithmetic and logic unit. It's going through a whole bunch of stuff, right? So how do we actually connect this path from here to here and also from here to here? It's just a matter of selecting the switches, right? By Okay, I know this looks really kind of ugly, but by controlling this demultiplexer, I can now connect out 0 from the register bank to in 1 of the ALU. Okay, I'm not even concerned about the value of the selection. I'm just saying that there is a way to do it. When we look at out 1 of the register bank, we have to control this particular multiplexer, and in return, we also have to control this multiplexer, but there is a way to make that connection work. Is that okay? So what the ROM is doing is orchestrating all of these control bits to control the pathways between major components of the processor. Okay? Now when you look at the ALU, it has an output, okay, the result of the computation, the sum in this case. So the output has to go somewhere. If I want to store the result of the sum, of the addition back to a register, how do I do that? So what you need to do is look at this Y here. It goes through this multiplexer, but eventually there is a way to go back into the register bank to be stored. So now the question is, how should I configure this particular multiplexer so that it connects the output of the ALU into the input of the register bank? Okay? And how do we select which register is supposed to store the result? Well, we have RI select, register input select. This is going to specify which register should be updated. So, in other words, just by looking at this, those bits down here, okay, the really massive, ugly looking splitter is really nothing more than doing all the little things. Go like, okay, you connect over there, you connect over there, you connect over there, clock perform the operation. Next clock cycle, we move on to the next location in ROM, and we'll do something else.
It's like a control tower.
Exactly. This is Sir Topham Hatt. This is the solar island. and Sir Topham Hatt is basically just playing with all the tracks. Okay? This track needs to connect from here to here, that track connects from there to there, so that Thomas can go from this station to the depot over there, and so on and so forth. He's just operating his island. Yep.
Can this be classified as like a certain number of bits processor, an 8-bit processor?
This is an 8-bit processor because when you look at, so when you specify whether a processor is 8-bit, 16, 32, or 64-bit, it has to do with the ALU. That is the usual way of defining the width of a processor. So when you look at the adder, the width of the adder typically defines the width of the processor. So when we talk about 32-bit processors, it means the adder inside the ALU can add 2 32-bit numbers at the same time. Instead of chopping it into 4 individual operations, it can add 2 32-bit integers in one single operation. So 64-bit processor, basically you can add 2 64-bit integers in one single clock. But today, I just really want you to look at the components and also just get an idea of what this is, okay? So I know most of you will just remember this part and not a single thing about the processor itself. So we'll look up the island of Sodar. Okay, I think that's the right name. Yeah, fictional island. And Sir Topham Hatt. There we go. There you go. So this is Sir Topham Hatt. And there's a picture of the island of Sodar and all the trains. But if you watch those movies, they have got tracked selectors, and they have places to connect. It's really one of the best analogy because if you look at cars and highways, it's not nearly as good as an analogy because you don't have the track selection mechanism. Whereas for trains, you have the track selection mechanism. And you basically want to improve the efficiency of the island as much as you can so that one train can go from here to here, and then another train can independently go from here to here, and so on and so forth.
So the ROM, it cycles through the instructions.
The ROM cycles through not the instructions, but what we call microcode.
Where the circuit is going. What happened? Does it just like cycle through continuously, or is it just like?
That's a very good question. So these do not, they're very short, okay, how should I put it? Sections of the ROM, one section forms a particular subroutine per se, okay? So which subroutine do you want to activate? That depends on the content of RAM. So this connects back to the volume and architecture, because what you're doing is you're storing your instruction or the opcode in RAM. Those opcode will go through the data bus. Okay, let me highlight the data bus here. It will go through the data bus and go through a few multiplexers and whatnot, but eventually it gets to the instruction register. The instruction register, the output of the instruction register, it ultimately connects to this pin, this tunnel over here, and eventually it becomes, you can use it to specify ucode PTR. So your opcode can initialize your microcode pointer so that you can basically use it to index which location of the ROM should be the starting point of operating that single opcode. In other words, Sir-Topham has some macros per se. Okay, are we undocking something at a dock? Okay, that becomes one quote-unquote macro operation. Are we transporting school kids from this town to a coastal city? Okay, those are macro operations. But what should this Sir-Topham head or the operator or the controller of this entire train operation? What should he be doing? Should he be sending kids to the coastal town? Should he be unloading fuel from a depot and transporting that back to the train station and whatnot? Those instructions come from RAM. So there's a particular this is programmable from the perspective of a programmer. On the other hand, just hold on 1 second. On the other hand, this is innate. It is not programmable from the perspective of the programmer. Yep.
So does each actual instruction correspond to a sequence of
yes.
pieces of that ROM?
Yep. Exactly. Yep.
At the beginning of the semester, when you were talking about the virus that affects all the processors or the processes, is this the person basically have the knowledge of the processor to the point where you can predict?
Not quite. Meltdown and Spectre rely on a race condition of the caching mechanism. In other words, it is exploiting a race condition, which has to do with is the control of whether you have access to a RAM location. Is the control signal faster, or can you get to the content faster? That is the essence of the Meltdown and also the Spectre security flaws. But this process is way too simple. It doesn't have a caching mechanism. Yep.
So then is it the address port just specifies a start point for each
yes.
instruction? Okay.
Exactly. It's indexing to the start point, and then so each instruction, each opcode has up to 16 microcode steps that you can specify. So far, the longest one is 2 steps. So I totally overestimated, how much is needed.
Does it have to step through all 16?
Huh?
Does it have to step through all
No.
16?
No, it doesn't have to step through all 16. But is the general idea okay so far? Okay, yep.
How many times more complicated is the processor?
Oh, way more. Way more. Much more than that. Much more than 1,000 times. Yep.
A processor is a really small thing, right?
Yes. It can be. It depends on which processor you're talking about. Okay. I think most of you, or some of you at least, remember that we talked about the 6502 processor on the Apple II computers. Yes? I was showing you guys the Strike Eagle, F-15 Strike Eagle flight simulation program or game. Remember that? Okay, so we'll take a look at this one and count and look at the transistor count of the 6502 processor. It is actually listed here. It's a very small number. It only has 3,510 transistors. That's a really, really simple design, because when you compare that to a modern, complex, the high-end i7, i9 processors, what is the transistor count on those things now? I know it's more than 10 billion, sorry.
Yeah, something.
I think it's 10 billion. In terms of order of magnitude, it is already in the 10 billion order of magnitude, as opposed to a few thousands. So that answers the question of how simple the design is. Now the 6502 is actually in a way simpler than the architecture that we are looking at, because it doesn't have general purpose registers. It has one single register instead of 4, and the instructions are actually simpler in some sense compared to the processor that we'll be using in Logisim. Let's see, what time is it? Okay, we got 7 more minutes, so I can actually show you the tool chain as well, so that you guys know, how you will be writing programs and how you'll be running your programs. Okay. All right. So the way you write your program is simple. Okay. You just go to any text editor. Okay, and in this case, I can use Mousepad. You can use Notepad in Windows, or VI, or whatever favorite text editor you want to use. It doesn't really matter what, okay? So, the syntax is also really easy. / starts comment, okay? So I preserve that in this particular language. So this is a test, okay? And you can have labels. Label definition ends with a colon. And then you can specify instructions. This is no op, which means no operation. And this is JMPI, which specified jump immediate. And I just jump back to the loop here. Okay, this is not the tightest loop ever possible, because of the no op. I'm just giving you an example of what a program looks like. Okay, and then we just copy this. Control C, Control A to select all, and then Control C to copy. And then you go back to the browser. Okay, where's my browser? There we go. And then you open up the assembler. Now this assembler is read-only to you, but you can make a copy of so that you can make changes to it. And you are correct. This is actually a Google spreadsheet, but it is actually an assembler as well. I implemented an assembler using a spreadsheet, basically. There's a little bit of documentation up here, a little README, but the source code is on the second tab. So you click on the second tab. There's usually a program here already, but you can just erase it. It is okay to erase the cells on column A, but not the other columns. So make sure that you do not erase column B or the other columns, because they actually have formulae and equations and stuff like that. So a single delete would delete the content. And just go back to the first one and do a Control V to paste. There we go. And after it pastes, you want to wait a little bit, wait till this bar is done computing. I have a really slow computer. Most computers can get this done in a fraction of a second, but mine is really slow. And then you go to RAM file. Now, if you do have a syntax error, it will show up, and you won't see v2.0 raw, okay? If there's no syntax error of any kind, then you will see that. So then what you do is you go here, you just go to File, you say Download As. You can use CSV or TSV, it doesn't really matter which one you choose, and give it a name. Okay, just go save the file. Don't open it in the spreadsheet, it's not going to do you any good. So we'll just say this is a test program. Click Save. So now we have the file saved. It's just a regular text file, there's nothing fancy about that file. Then you switch back to Logisim. And to be very sure, you want to click the reset button once to reset the processor. There we go. And then you go to the RAM module, right click, load image. And then you just go to wherever you saved that file earlier. And I cannot remember at all where I saved it. So I'm gonna check, nope, temp folder. It doesn't let me specify the path in one single shot. So, okay, should be here, test, yep, right there. Click open, And you can see how the program is loaded. It doesn't look like it's loaded, but it is, okay? As it turns out, the no opcode is 0, 0, okay? And then the jump instruction is a 4, 0 followed by 0, 0. So that's why we do have 3 bytes in this particular program. It just doesn't look like it has loaded the program. Okay. So when you run the program, you have a few choices. You can do a single click, per clock. When you're debugging the program, that is recommended. But if you kind of know what the program is supposed to do, you can just go to simulate, specify a frequency that is visible. 32, 16, those are kind of visible. So I'm going to pick 16 here. And then you want to go to a particular portion of this processor where some change is observable. One thing that should be highly observable is how the program counter is changing. The program counter is what is controlling what location in RAM you are reading the opcode. Okay, so it should go from location 1 to location 0 to location 1, and then back to location 0, back to location 1, back and forth like that. Okay, so that should be the visible aspect of running this program. So you go to simulate, and then you enable the text so that you don't have to click a lot. Okay, and the program is now running. You can see how the program counter is going 0, 1, 2, 0, 1, 2, 0, 1, 2 because it's a type. So the program is running at this point.
There's no condition for it yet. According to the program that you put in, it's just going to loop endlessly.
It is just going to loop endlessly. That is correct. So that is one thing. And then since you have time to read this before Thursday, so the other thing you can also do is to go to the processor folder and read the assembler manual, which describes how to use the assembler. Okay, let me double click it. It's just a regular word processing document in this case, so there's no tricky stuff here. Okay, it starts with copyright stuff, how to use it, and it also describes these instructions. Let me just zoom in a little bit because I want you guys to see how I document each individual instruction. Okay, so each individual instruction is commented using the equivalent C structure or the equivalent C constructs. The whole instruction is represented by a for loop with semicolon, semicolon inside the parentheses, and a semicolon outside of that. What does that mean? What do you think it means? You're not going to go anywhere. If you have code after this, it's not going to execute. In other words, when execution reaches a halt instruction, it just stops. You can keep clocking all you want, but the execution is not going to get out of the halt instruction itself. Okay? The no halt instruction is represented by open and close curly brace. What does that do in the C program? Nothing. Absolutely nothing. Right? Okay? That's what the no op is. Okay? That no operation doesn't do a single thing. Add XY. X has to be a register, which is ABCD. Y has to be a register, which also can be ABCD. The operation is X plus equal Y, which is a compound assignment operation. It is the same thing as X equals to X plus Y. Okay? And the same applies to most of the other ALU type instructions. ALU type instruction, no change to flags. Increment X is auto-incrementing. Decrement X is auto-decrement. Okay, no big deal. Copying type instruction, LDI, load immediate, XI is basically saying X equals to I. But in reality, what it is doing is it's saying register X gets whatever the program counter is pointing to, and then you add 1 to the program counter. I'll explain that later in this class. You can do indirect. In other words, you can use ST and LD instructions to affect content of memory. This is the only way they can store something or load something from RAM. Okay, is to use a register to specify where, and then another register to specify the value. So when you have STYX, it is the same thing as dereferencing Y, and whatever Y is pointing to, store whatever X has in it. And then load is the opposite. So you can see how load is exactly the opposite. X equals to dereferencing Y. Whatever Y is pointing to in RAM, get that content, store it into register X. Is that okay? And here's the fun part, okay? It took us this long to start to understand, oh, why did we talk about the flags? This is why. Okay, now, I may not have talked about the Z flag, okay, we just talked about it today, but you recognize all of the other ones, don't you? The carry flag, the sign flag, the overflow, and the L flag, okay? This is the only way you can do conditional branching in assembly. There's no loop, no conditional statements, it is just conditional branching. And conditional branching is very, very limited as well, because you're only controlling the program counter. You're basically saying the program counter is going to be whatever X is, which is a register in this case, or it doesn't change. In other words, you just move on to the next instruction. That's the only way you can make decisions in assembly language programming. And you might think, but that's only because you're cheap tack, you shortchanged us by trying to reduce the number of transistors. No, I can tell you all processors are like this, okay? The only way you can make decision is to look at a single flag and go like, should I continue execution with the next instruction, or am I going to go somewhere else? That's the only way you can do branching. Yep.
The C is the carry out flag.
Yes, C is carry out, Z is the zero flag that we just talked about earlier, the NOR gate, the NOR gate. S is sign, O is overflow, L is the L flag.
So if the carry out flag is 1, we're going to assign it the new value.
We are going to change the program counter to whatever register X has. X is a register, one of the ABCD registers. Yep. So you can probably imagine that your conditional statements is going to get a lot longer than you're used to. Your loops will get a lot longer than you're used to. So we will talk about systematically how to write code in this assembly language. If I give you the C code, I will tell you how to translate that into assembly code. It's a very structured approach. Okay, so it's not like there's some black magic and dark science in it. Okay, it's very, very mechanical. It's boring. We'll also talk about parameters, local variables, how recursion is done, how do we pass a return value back to the caller. All of those concepts in C and C++ will be implemented using these instructions, and you'll be running those programs using Logisim, using that toy processor thing. That's what we'll be doing for the next 8 weeks or so. Yes. Is that what you have been waiting for?
I'm enjoying this hardware stuff. I'm going to be into computer engineering, so this has been a lot of fun.
It is kind of fun because because of the transparency. Most classes teaching this type of thing, they just give you the assembler for the i386 for the processor architecture, and just run it, but you have no idea what is going on behind the scenes. Yep.
I want to point out to everyone that you went way too far. You didn't have to do any of this for this class. We are in a community college, and you did this? I just want to point that out. That's freaking incredible.
It is a lot of fun for me.
That's incredible.
This is what I do for fun. A little sick, I guess.
I don't know, I'm just saying, am I the only one impressed here? Because we're in a community college and this doesn't happen.
No, it is impressive.
So I'm just saying.
Well, thank you. I'm glad that you guys will find it useful. You guys are making me blush because it is not. There's no logic in it, right? So, but the nice thing about this is if you so I'm going to stop the simulation. If there is one place, of one particular opcode you do not understand how it works, you stop the simulation in one single frame, and then you can poke each component, each wire, and figure out how does it get it done. That is the whole purpose of doing this entire thing in Logisim, is to give you that transparency. It's kind of like one of those models. I'm not sure whether you guys played with those models when you were kids. It's kind of like the transparent engine block with all the valves and all the crankshafts and whatnot. And you can just rotate the engine just a little bit, and you can see which valve is lifted and in whether the cylinder is compressing or decompressing and all kinds of stuff like that, it's for that purpose, because you now have complete visibility of what is going on inside this particular toy processor. So I'm hoping that this will be helpful to kind of illustrate the organization and architecture of the processor. All right? Well, we're running out of time, so I'm going to let you guys go, and I will go at the lab later today.